Hello, and welcome to the Argyle AI ML Technology Leadership Summit. My name is Nick Ciavata with Argyle, and it's great to have everyone joining us today. I have some important information to share with you, and then we'll turn the floor over to our esteemed opening keynote speaker. First, we would like to take a moment to thank today's sponsors, Eightfold AI. Our sponsors are committed to providing you with valuable content and a great overall experience. At any time during today's event, you can visit their virtual booths from the main agenda page, which include complimentary materials, information, and meet and greet opportunities. We also welcome you to stay socially connected during today's event. For those of you who are active tweeters, please use the hashtag ArgyleDigital and follow us on Twitter at Argyle Exec Forum. Also, be sure to follow Argyle on LinkedIn for special announcements. I would like to take a moment to touch on our content neutrality policy, which we have curated based on the feedback we have received over the years from our members. We have worked closely with our speaking faculty to ensure that you receive a set of balanced and neutral viewpoints during the session today, and we appreciate our members' support of this policy. Finally, and most importantly, we want to hear from you. So during each session, we encourage you to submit your questions and comments in the Q&A box on your screen. Following each presentation, we have set aside time for our speakers to weigh in on your questions. Thank you again for joining us today. Now, let's get started. Without further ado, I would like to introduce Manny Gonzalez Rivero, Director of Applied Machine Learning, Maxar Technologies. We're really excited to have Manny for his opening keynote presentation titled Scaling AI ML, Improving the Cost and Speed of Data Analysis with Just-in-Time Modeling. Welcome, Manny. Over to you.
Thanks, Nicholas. I'd like to thank Argyle and the sponsors for giving us the forum here to talk today. So thanks for that. So what we're looking to talk about today is really around how we start scaling AI and ML solutions while trying to improve the cost and speed at which we do data analysis. And we're really looking at this concept called just-in-time modeling in order to do that. What is just-in-time modeling? Just-in-time modeling is this concept that you're able to actually produce models and inferences and insights for our customers at the speed at which they can think of the outcomes that they'd like to achieve, right? Just-in-time itself can be quite nebulous, but it's really driven by the use cases of the different customers. And we can talk a little bit as we go through today around what exactly that means for us at Maxar. Maxar itself is a company that needs to process terabytes and terabytes of data on a weekly basis. And it's not uncommon for our data holdings to be in the petabyte scale. And so it really is truly a big data problem. And we're really trying to help our customers find, these insights within an enormous haystack of data that seems to be growing all the time. So what we're going to talk about first is, kind of these 4 axioms or trends that we're noticing and how that drives a hypothesis around how we think companies are going to make money in the future. And we're going to talk about how just-in-time modeling is a logical conclusion for what we should try to pursue in order to meet that hypothesis for improving profitability at our company, right? And then we're going to talk about what are the key investments that we have to make in our infrastructure in machine learning in order to enable these ideas around just-in-time modeling and then ultimately helping our customers, right? So without further ado, the first axiom that we'd like to talk about is probably not going to surprise very many people, but Moore's law is a pretty persistent force in our daily lives as engineers now, right? It's not an accident, though, that multi-layer perceptrons or perceptrons itself were kind of invented in the late 50s, like 1957. But yet it still took about 65 years, or really 60 years or so, for concepts around deep learning to really take hold. And a big part of that is because we didn't have the compute costs really at a level where folks could at a broad creative capital scale exploit the ideas around neural networks and deep learning. And so we continue to see this trend improve. And it really lets us start to think about, well, what are the kinds of things we might be able to achieve as that compute gets more and more dense and more available. The second one is the notion that the cost of memory is also going to zero. Now on a per terabyte scale, it's probably a handful of dollars for disk. But more importantly, solid state is also coming down at an interesting and dramatic level. And the reason that's important is that solid state enables us to feed more and more data more and more rapidly into our ever cheaper compute that we just talked about in the previous slide. And that really starts hitting our ability to be more reactive and quick about how we feed data into compute centers where we can do modeling, right? The third concept that we have is, and this is a significant, admittedly, much more, this is definitely a conjecture more than anything, but I think we are seeing that the cost of power could also potentially start getting closer and closer to zero, particularly as we start seeing more investments in photovoltaics and start seeing more and more energy going back into the grid. It is a conjecture, but it's possible that the cost of power could also be going to zero. Finally, it's something that's not going to surprise a lot of folks. Data is also growing exponentially. And the reason that's important is basically that as data becomes more and more available to folks, it does allow you to drive more and more decision making. However, there is a notion that your ability to profit from information goes down as data becomes more available to everybody. And so for instance, if you think about a day trader or somebody on Wall Street, if everybody knew that tomorrow the price of some stock were going to be at value X, it would actually be very difficult to profit off of that information because everybody would be baking that into their assumptions. And so what that means is that you basically have to find novel information in this increasingly growing, data source or data pile that we're building, and that can be quite challenging, from an infrastructure perspective. So, what does that mean exactly? So, the hypothesis that those four things drive is the idea that a company that minimizes the costs of its means to acquire and exploit novel data sources is going to be very successful in the coming years here. And the follow-on point to that is that if you want to reduce the time and cost required to make new models to deliver insights to your customers, we believe that the concept of just-in-time modeling is going to drive a lot of that outcome. And so again, what kind of is included in the concept of just-in-time modeling? It includes your ability to wrangle data very rapidly. It includes your ability to create models at a time scale that are relevant to your users. It includes the ability to push that information out into production for your customers to exploit. And then oftentimes continue to update those models at the same speeds so that the insights that you generate are continually relevant to your customers, right? So then the question is, one question that's asked to me oftentimes as a director of data science at Maxar is, how do we actually want to focus our resources so that, both in labor and in capital, in order to make that outcome happen much more rapidly? And we're talking about on the scale of quarters, not years and decades, right? So what are the key bets that we have to make as a company in order to enable that outcome? Well, we're really looking at ideas like machine learning operations pipelines, infrastructure. We're looking at the ability to do data set engineering and enable what we call data fabrics. We're looking at concepts called label factories. We're looking at model quantization, and we're looking at inference engines so that we can execute these production pipelines, at the extreme edge and things like that. So we'll talk a little bit more about what each of those concepts are from the Maxar perspective. So when we talk about AML ops, applied machine learning, that's what AML stands for. When we talk about these operations pipelines, what exactly are we trying to enable? What we found is that one of the biggest impediments to moving models into production rapidly was the fact that we were asking our data scientists to do too much. We were asking them to be cloud infrastructure specialists. We were asking them to be software engineers. We were asking them to be statisticians, subject matter experts, oftentimes physicists. And finding an individual that has all of those capabilities in one place so that you can rapidly go to production is actually rather difficult. And if you find someone who is that way or train somebody to gather all of those competencies, then generally they'll get hired away by companies that have much deeper pockets than ours. And then you're back to square one. And so the concept of investing in machine learning operations pipelines is really about separating those duties into different individuals and creating infrastructure that allows them to interact in a way that gives you that unicorn capability, but distributes it across many different individuals and really allows those folks to focus and grow within those career tracks, right? What exactly are we talking about in terms of separations? Well, we think about the infrastructure kind of in three tiers. We think about the base, which is cloud infrastructure, ML ops. It's the ability to wrangle large-scale compute either on-prem or in the cloud very easily. There's a layer of machine learning engineering, and that is a software layer that sits on top of that ML ops layer that really enables folks to, in a few lines of code, train tens or hundreds of models, create or generate hundreds and thousands of data sets that can be exploited for training and analyze the results of models at scale. And then you have that third layer at the top, which is the data scientist. And that's really the tip of the spear. That's the person who really does understand, the nuances of neural networks, understands how they might fine tune or train or drive large scale experimentation by exploiting, this platform that we've built. And, so that really, when we start doing that, what happens is that you can really go from concept in through Jupyter, generating models, and then ensuring that those models go into production and can produce, can process, terabyte scale data to produce insights that matter for our customers effectively. One good metric here is, when we first started investment a few years ago in this, when a data scientist came into the company at Maxar to try to look at data and train a model, that oftentimes was measured in the scope of weeks and quarters. And now, if you were to join Maxar, you come in with your authentication badge, within about an hour and a half to 2 hours, you can make a model that is production ready and can be in production. And so that really starts changing the game in terms of how many customers you can meet and the type of investment that return on investment you can get from this infrastructure. The second concept we want to talk about was the notion of the data fabric. So what we found is, we have a very large company. We're 4,000 people. It's highly distributed. We have hundreds and hundreds of projects that are being executed against this workforce. And oftentimes when those workforces go and execute against labor, the way that they gather and maintain their data sets can be very highly varied. So on the one hand, you might have folks who are very sophisticated and they're using Postgres, PostGIS, or they're using their own forms of data fabrics. On the other hand, you might have folks who are literally storing data like in a folder, and so that actually makes it rather difficult to exploit a lot of the different data sets and hard work and human capital that's being put into solving these problems. And so what we've invested in is a notion called a data fabric. And what that does is it allows us to abstract how people access information across the company, so that in a few lines of code, you can actually download information that are stored in a wide variety of ways. And it creates that adaptation to allow to go from those varied forms into a canonical format that can be accessed very rapidly, right? This is extremely important because as we make data more indexable and accessible, it helps us, operate in more sophisticated ways. For example, we've started working on this idea called statistical query. So when you are a data scientist and you're sitting there and you're trying to figure out, how do I make a data set that makes it so that the training set is as homogeneous as possible to the test set, in other words, where I need to go into production. And we've actually created the ability for folks to define the data sets in terms of a large set of parameters around its characteristics. So for instance, if you wanted to make an object detection model and you needed it to be 25% black cars, 50% aircraft, you wanted it to all exist over Brazil, between the dates of December 1st to December 30th, that actually becomes a very difficult traveling salesman problem where you're trying to push the data into those data sets. Because you're also constrained by how much you can push into the GPU. And so using something like a data fabric actually enables us to very rapidly conduct these statistical queries, produce thousands of candidate data sets, compare their characteristics to the target, and use some sort of Monte Carlo sampling to find the absolute best data set that matches the test target effectively. So that's been really quite a boon and has helped us quite a bit in terms of our ability to manage these data sets. And then finally, once you've figured out that layer of infrastructure and that layer of data access and data transport, really what we found is the largest impediment to rapid modeling, to enabling just-in-time modeling, is the notion of the human capital required to build data sets that matter, for our customers. So that would be, we talked about statistical query. That would be producing the metadata effectively and the samples that could be queried upon to meet the customer needs. And so we've invested in something that's called a label factory, and that really automates as much as possible the communication between the data scientist who has an intent and what they would like to have built, all the way down to the human capital that is producing the actual labels themselves. And what that does is it allows us to produce tens of thousands of labels in very short order, very, very short order. And once we've produced that OV1 of the data set, the version 1 of the data set, it actually allows us to iterate so that the data scientists can say, that did or didn't meet the mark on a basis of a set of statistical parameters, right? And so when you start closing that loop, you really start being able to produce the data sets that you need and hone in on the homogeneity you require with your targets. And so what we've done here is we've taken our human capital. We have many different sources of human capital from different parts of the company, internal and external, in different enclaves. And we've created interfaces that allow us to communicate with them really rapidly. And they themselves also have their own application layers that allow them to meet different labeling missions as well. And so all of that to be with the intent of being to reduce the time cycle between a data scientist having an idea to being able to marshal the human labor required to build those data sets. So those seem to be a lot of the mechanics related to just enabling just-in-time modeling. We also have a concept about trying to make more quick the literal execution and modeling or training of the models. And there's a relationship between the number of parameters that you need to conduct a model and the amount of time it takes to train that model, and also the amount of data required to train that model. So what we found is by investing in a concept called quantization-aware training, we're able to take models and reduce them orders of magnitude in size without compromising the performance characteristics of that model. And so, for example, if you have a 32-bit YOLO v5 model, that's roughly 32 megabytes in size if it's the small variant. And if you use quantization-aware training where you're using just enough bits in your weights and biases to drive those different to drive your model, you can get that down to a handful of megabytes, sometimes hundreds of kilobytes, right? So now you're dealing in a bit and cycle accurate space instead of a 32-bit floating point number space, but you're able to get a shocking amount of performance, from these quantization-aware methodologies. Now, why do we actually care about doing that? Well, if we're able to do that, we can then start moving the inference into different substrates. So traditionally, we might have, pushed a lot of this modeling into a GPU, and that's kind of what folks are comfortable with, right? If people are generally modeling, on cloud infrastructure, it's very common that they may pull up a GPU instance and they can execute there. Most GPUs, though, they will have a 32-bit mode. Maybe they'll have a 16-bit mode. Very rarely will you see an 8-bit mode, right? On the other hand, if you move into something called field programmable gate arrays, which are basically configurable application-specific integrated circuits, ASICs, you can actually start being very prescriptive about down to the bit level how your hardware is configured to allow you to execute inference. And what that does is it reduces the power required to execute those models by about a factor of 10. And it increases the speed at which you can execute models by about a factor of 6, we're finding. And so what that means is using our machine learning engineering infrastructure, we're able to target inference engines that produce models that can execute at the extreme edge. Why would we want to do that? Well, Maxar is a company that has satellites in space, taking pictures of the Earth, and we find it really advantageous to start moving that modeling onto the birds, onto those satellites. The reason being, if you're able to understand the quality of your data, or what the content of your data is really telling you, what is the knowledge contained within that data, you're able to do a lot of extreme amounts of compression on that imagery and really reduce the amount of bandwidth you need to send data down more rapidly and reduce the timeline it takes for you to go from the satellite down to the insight that you want to come to on the ground, right? And so we found that that going through this process has allowed us to run inference at twice the rate of capture of these sensors. So you have an imaging sensor up in space, it's taking pictures of the Earth. That's operating, at extreme speeds, I can't say. But we're now able to actually execute modeling at twice that speed on a footprint that where we could conduct hundreds of models at a time simultaneously. And so now we're actually able to understand the content of that data right at the point of capture. And that really drives, distribution decisions downstream, which can be quite helpful. So all of this is to say that all of these technologies that we're investing in are really starting to defeat those long time cycles that we've been looking at traditionally. When we start talking about our ability to meet a customer need, as I said previously, we were talking about the 6-week time frame, half quarter to a quarter time frame, depending on the complexity. And now, as a result of this kind of training paradigm, instead of taking hours per model to train, like 2 to 3, 4 hours per model to train, we're really looking at a handful of minutes. And I really only see that getting better. And that is entirely tied to your ability to access data, engineer it properly, access compute, and push that data set into that compute framework properly. Use the correct types of models that will enable very rapid training and execution and inference, and allow those to be executed at the extreme edge on the fastest hardware we have available. And so that's where we are today. It's going to be interesting to see what happens in the next 5 years, I think, as the technology and those trends start exacerbating, and proving out these theories. So I guess what you should ask yourself is, in the context of, this thought experiment, what can you do today to lower the time and cost of acquiring and exploiting data for your business or your customers? And if you imagined a world where, an individual could train like a ChatGPT level model every month, every week, every day, hundreds of times a day, what could be possible? What does that actually enable? I think that's where we're headed. And I think it's a very exciting time, certainly, to be alive in this space. And so, looking forward to seeing what people do with this moving forward. So with that, I'll pass it over to Lindsay.
Great. Thank you, Manny. We have some questions from the audience. Let's see here. I'm going to pick a good one. Someone asked, how soon can we leverage ML to automate manual data collection from various changing file formats into structured data sets?
Yeah, that's absolutely the right question to ask, right? Because as you notice, we've got, as I said, we're investing in these things called label factories to utilize more and more human capital more effectively. I don't think it's going to go away completely. I think the other half of your question, right? On the one hand, you're saying, how do I produce labels for unstructured data, right? Automatically, so that I don't have to rely on human capital. That's one way to think about it. Another way to think about it might be to flip the problem on its head and say, how do I start with labels and generate synthetic data that is similar to my target phenomenology, right? So you see a lot of kind of work being done there right now in synthetics. People are using GANs and different techniques to be able to generate rich data. It really depends on how complicated the underlying phenomenology is. In the case of satellite imagery, a single image represents millions of variables, and it's imaging something that's really quite complex, the Earth itself. But I do see a world in which we start with some sort of a map, like a Google map or something like that, or a Bing map, whatever it might be, that describes what the Earth might look like from a mapping perspective, and go from there to generating input imagery that we could then pass to the GPU to teach it, how to find certain objects of interest, right? So I think that The challenging part is, even if you are automating the ability to go from unstructured data to structured data, that automation itself will also require some amount of training. And the tricky part with that is that it's very rare to find problems that are wide sense stationary, meaning that the phenomenology underneath you isn't changing. If it's changing, then you also have to take into account, how do I model that change in terms of creating structured data? So that becomes quite challenging. I think we're getting pretty close. I think there's a lot of work, and with everything, I don't think there's going to be a magic switch that turns off. This is okay, now we've done it. I think it's going to be about interrogating these different problems and finding subsets of the problem that we can solve.
Great. And here's another question. Do you find security protocols or ethical concerns hinder your AI/ML progress?
Uh, it's a very interesting question. I don't think that is the case. I think that we ought to be very considerate around how people want to use technologies like AI ML. And it's really important that in my view, that we listen to everybody around this, and ensure that these technologies are not being abused. And so I don't ever think of it as a hindrance. I sort of take the axiom of slow is smooth, smooth is fast. And so I think an event that is catastrophic would be much worse for the industry in the long term, as opposed to doing the right thing up front. So that's kind of my view.
Okay.
But personal
Great.
view, by the way, very personal view. Yeah.
Understood. All right, here's another question. How much governance do we need for AI ML to prevent the negative impact to organizations?
Yeah, that's a really it's a really good question. I think, to me, you ought to evaluate the impact of failing at governance, right? And then in a world where I have to make a lot of funding decisions, in a world where you have to decide how much money to allocate to that, or people to allocate to that, you should make an investment that's commensurate to the impact and the risk. So that might sound generic, but not knowing your specific problem, I think you really do have to understand what is the cost of being wrong and getting it wrong, and then apply investments appropriately.
Great. All right. I think we have time for another question. Here's one. Who should lead the AI governance efforts in the company?
That's a great question too. I think it's a bit of an arms race, in a sense that right now, historically, if you look at what we've invested in, the AI capabilities, or the machine learning capabilities, have far outstripped our ability to govern it, right? And so I think that it's important to separate those two capabilities and incentivize them appropriately. So it's not necessarily true that the folks who are producing the models should be the ones that are governing those models. And so, I think it's important to have that separation, but it is important even more so to equally fund those capabilities. And so it's a bit of a tragedy of commons. Nobody minds when everything's going well, but when something breaks, everybody complains about governance, right? So we need to make sure that we're investing in that appropriately, equal measures, early and upfront.
Okay, great. And I think we have time for one more question. Do you have any hiccups with AI with cloud/hardware performance?
Oh yeah, for sure. Well, I mean, one thing is that cloud can be quite expensive, right? And admittedly, they're maintaining it for you, and if you're paying an external service, that can be quite expensive, right? And so one thing that we try to do is try to leverage as much on-premise resources as possible while staying up to date, and that means investing in technologies like Kubernetes in order to normalize the hardware platform that we're deploying against, right? So overcoming that is one. The second one is that sometimes we're in enclaves where cloud doesn't exist, right? If you are building an application-specific integrated circuit that's going in space, there's no notion of cloud there. And so you can get into a space where perhaps you overinvest in the idea that cloud will always be available. And there's many notable cases where it's not of importance. And so it's important also to make sure you build infrastructure that's not overly reliant on any one provider, in my opinion. And that'll de-risk you from overly expensive providers.
Great. Well, thanks again, Manny, for an excellent keynote. I also want to thank everyone else for joining us today. This session, along with all of today's content, will be available on demand following the event. Have a great day.